Okay, log functions. Logs are inverses of exponential functions. When we get exponential functions, when we graph them, exponentials have horizontal asymptotes. When we get to the graphing part of this section, you'll see that logs have a vertical asymptote. Okay, it's the reverse. Okay, inverse means it's like the reverse function. Okay, so addition and subtraction are inverse functions. Multiplication and division are inverse functions. Square roots and something squared is an inverse function. Okay, so if we have exponentials and logs, if you have both of them combined, they're going to cancel each other out, right? Just like if you have addition and subtraction, they cancel each other out, right? So two properties that you need to know, you need to understand in order to be able to work these problems is that first you need to understand that the base for a log is the same thing as the base for the exponent. Okay? This is read log base b of whatever. Okay? So if it looked like this, we would read this log base 7 of 3. It's log base whatever of whatever. Okay? And so when you hear me say log base something, it's because that's the base. Okay? But if I'm changing it to exponential form, that base is still going to stay the same. So log base b of b to the x. Now, this is saying that those two are the same. Whatever the base is, it's the same. Okay? Log base b of b to the x equals x. Okay, that's a property you need to know. So what happens is this log base b and this b cancel each other out, leaving you with only that exponent. Okay? Likewise, if you have a base and it's raised to log base b of x, that also equals x. This and this cancel each other out. Okay? So if I had, now this section right here is explaining how we get from here to here. Because this log base b of y equals x is the same thing as y equals b to the x. Those two are interchangeable. Okay, they're the same thing. And this is showing you how they did that. So if I do something to one side of the equal sign, I have to do it to the other. Correct? So let's say I take this base, and I'm going to take this, and I'm going to change it to exponential form, which means I'm going to use this base as the base for the exponent. But if I do that on the left, I have to do it on the right. So I'm going to take this base right here, and I'm going to make it my base, and I'm going to raise it to this power on the left and to this power on the right. Okay? So I say b to the log base b of y equals b to the x. Well, according to this property right here, b to the log base b of y, this b and this log base b cancel each other out, leaving you with just y. Okay? So we say y equals b to the x. That's important because, God bless you, in the next section it says rewrite the log functions as an exponential function. So they're going to give you a log function. We're not solving anything. All we're doing is rewriting it. We're going to practice going back and forth from log form to exponential form, and then from exponential form back to log form. Okay? Because if your variable that you're solving for, which we'll do in section 8.6, if the variable that you're solving for is trapped in an exponent, the only way to get it out is to change it to log form. And if your variable is trapped inside a log, the only way to get it out is to change it to exponential form. Okay? That will release it for you. So you have to practice this skill first. Okay? Now, so what we're going to do is, so if we have log base b of y equals x, we've shown, now b, y, and x will be numbered. Okay? These aren't variables, they'll just be numbered. Okay? We've shown that we can take and go straight from here to here to write it in exponential form. In other words, this base for this log is the same thing as the base for the exponent. This, whatever that log equals, is your exponent that belongs to that base. So we'll say b to the x power equals y. Okay? So you don't have to go through this whole long process when you're going from logs to exponentials. You can just look at that base for that log. Okay, so I'm going to do this one. The first one I'm going to do it the long way, and the second one we'll just jump straight to the shortcut. Okay? So what I can do, remember I said if I do the same thing on one side, I have to do it to the other, right? What's my base for this log? 6. So I'm going to rewrite both sides in exponential form using 6 as my base. Okay? So I say 6 to the, make that your power, log base 6 of 36 equals, I have to do the same thing on the other side, 6 to the second power. All right? Okay, remember our properties that we did at the top? If we have 6 log 6, what happens to those? They cancel, leaving me with just what on the left? 36 equals 6 to the second power. That is this log rewritten in exponential form. Now, eventually, you can skip that middle step. You'll start to see 6 to the second power equals 36. So if you remember that the base for your log is the same thing as the base for your exponent, and your log always equals the exponent. Okay? So let's do number 2 without going through the long process. Let's just jump straight to the exponential form. So what's my base? So the base for my exponent is 16. What's my exponent? It always, the log always equals whatever the exponent is. So what's my exponent for 16? 3/4 equals 8. Now, if you would like, you could do this middle step every time. So we would do 16 to the log 16, log base 16 of 8 equals 16 to the 3/4. And then your 16 to the log base 16, those will cancel, leaving you with just 8 equals 16 to the 3/4. Okay? If you want, you can do that middle step every single time. So we put both sides in exponential form, and then that's what happens. Any questions?
Is it 36 and 8 are those exponents or what?
Just to make sure, let's say I had how would I write that in exponential form?
49.
So yeah, so we can say 49 equals 7 to the second power. That has to be true. It is. 7 squared is 49. Right? But they're not always that easy to see. Okay? So if I had how would I write that? Good. 100 equals 10 to the second power. Okay? What if they give it to us like this and they want us to write it in log form? So they give us the exponential form and they want us to write it in log form. Well, when we were given the log form, when we did the long way, we changed both the left side and the right side to exponential, correct? And so if we're given both sides in exponentials, what do you think we're going to do? Change both sides to log form, okay? That's what we'll do. So So for number 3 and number 4, it wants us to take the exponential form and rewrite it in log form. I don't really have a shortcut for this way. All we're going to do, it's in exponential form right now. We're going to take the log of both sides. The base for our log is going to be the same as our base in our exponent, in our exponential. Okay? When you write log of both sides, you have to put a base. That base is going to be this. That's your base. The base for your exponential is the same thing as the base for your log. So, we'll take the log of both sides. Log base what? No, right, but log base 2 of both sides. Okay? So, log base 2 of 2 to the 4th power equals log base 2 of 16. As long as you do it to both sides, it's okay. Now, that first property, the very first thing you wrote down, log base b of b to the whatever power is equal to what that power is, right? So, log base 2 of 2, those cancel, leaving me with just what? 4 on the left equals log base 2 of 16. And look, I can check to make sure it's right. 2 to the 4th power equals 16. These, our very first property, showed us that those will cancel each other out. No. You're going to take the log base what of both sides? Log base 4 of both sides. All right. So we're going to take the log base 4 of both sides. Log base 4 of 4 to the 3rd equals log base 4 of 64. Well, these cancel each other out, leaving you with just 3 equals log base 4 of 64. Notice that now here, there's no variables, right? They're all just, everything's numbers. The base, the exponent, everything's numbers, right? But if my variable was right here, so this was 2 to the x power, and you see how it's beneficial to change it from this form down to this form? Because what happened to my exponent? It ended up right here, right? So if this was x, if 4 was x, then it would be x equals this. You understand? So that's the reason why we learn to go back and forth between these two forms, because it's the only way to release that exponent. Okay, and if there's a variable in your exponent, that's what you have to do to solve it. Okay? And the other way around too. If you have the log, let's say my exponent was in here. That's the way to get it out, is to change it from log form to exponential form. That separates that log. Okay, it's the only way to do that. Any questions? There are 2 special types of logs. Okay? In your calculator, when you hit the log button, you don't see a base. There's an imaginary base. Okay, it's not really an imaginary number. The base is 10. If you just see log of something, like right here, log of 100, there's an imaginary base of 10 right there. They just don't put it. That's called the common log. The common log is base 10, and you don't write base 10. Although you could, but if you don't see a base, that means it's base 10. The natural log, which there's the ln button in your calculator, that is a regular log base e. Remember, e is just a number. We talked about e last time. So that's just log base e. So if you see ln of some number, That's just log base E of that number, okay? Ln just stands for natural log, which means base E. Your calculator has a log button, and it has an ln button. So you can only use that log button in your calculator if it's base 10. If it's base something else, I have to show you how to do that. Okay, so this is called the change of base formula. Oh, it's not really a formula, but change of base formula. So let's say you have log base B of A. Okay, so B can be any number, and A can be any number. We can rewrite that using common logs. And what you do is you say the log of A divided by the log of B. And it's the common log of A divided by the common log of B. So you won't have this 10. Your calculator, you'll just do log of whatever, log of A divided by log of B. And you just calculate that. But that allows you to take something where you normally couldn't use your calculator for and change it to common log so that you can. Okay? Now, when we look at number 5, that has a different base. It's not 10 and it's not E, right? So we can't just put it in our calculator. So what we're going to do is we're going to use our change of base formula to rewrite it using common logs. So that equals log of -2 divided by log of 2. Now that's common log, so they're base 10. I just don't need to write the base 10. Now we're going to put it in our calculator. You're going to do log of -2 divided by log of 2. What do y'all get? You get error, right? I wonder why. There's no number out here that could make this true. I wonder why. No, they have to be the same. So think about it. Think about it. When you have a log, it equals the exponent, right? So what this is saying is, if I take 2, what power can I raise it to where my answer is -2? 2 to the -1 power is -2? Can you take a number and raise it to a power and get a negative number? Ever? No. You can't ever take a number and raise it to a power and get a negative number. That's not possible. So you can't take the log of a negative number. It'll get error every time. Okay? If I took this and said, let's change it back to exponential form, it would be 2 to the question mark equals -2. And there's nothing that satisfies that. Okay? There's no power that can equal -2. Okay, let's look at number 6. So how do I write this in natural log form? Log of 104 divided by log of 4. So log of the number divided by the log of the base. That's the change of base formula. Now you can calculate that. Round it to 2 places after the decimal. And here's 100. What'd y'all get? 3.35. Approximately. So if we took 4 and raised it to that power, it would equal 104. Okay, let's look at number 7. What's the base for number 7? 10. So can I just, do I need to do the change of base formula? No. Just calculate that. Log of 17. Straight up in your calculator. Log of 17. Now, you could do change of base. It would be log of 17 divided by log of 10. But you don't need to do that. And what about number 8? Do I need to change anything, or I can just use the LN button in my calculator, correct? The LN button in your calculator, the natural log button, right above, right underneath log. It says LN. So just do LN of 24. This is the same thing as log base E of 24. That's the same thing. Just called the natural log. So if you ever see log base E, you can use the LN button for that. Okay? Okay. The next section, they're going to give us a function, and we're going to have to find the inverse. Do you remember how to find the inverse? There were 2 steps. First, switch x and y, and then step 2, solve for y. Do you remember that? So this is just going to be manipulation. All right? Find the inverse. Switch x and y, and then solve for y. So if I start off with a log, and I'm finding the inverse, what type of function will I end up with at the end? An exponential. If I start off with an exponential, and I'm finding the inverse, what type of function do you think I'll end up with at the end? A log, okay? Logs and inverses are exponentials. Step 1, switch x and y. So this will be x equals log base 9 of y. Step 2, solve for y. We need to change both sides to exponential form. Okay? So my base is 9. So both sides, I'm going to do 9 to the whatever right here is power. Okay? So we'll do 9 to the x power equals 9 to the log base 9 of y. What do you think happens next? Right. 9 to the log base 9 cancels, leaving me with just what? Leaving me with just y equals 9 to the x power. That's it. That's why we use the same base. The base for the log has to match the base for the exponent, and then they cancel. That's why we use the same base, so that happens. Okay, so this is the inverse, and remember, you might see that written with the little -1. That just means the inverse of y. Okay? You don't have to put that, though. So we started with a log, the inverse was the exponential. Okay? Now, number 2, switch x and y. So this is x equals, that just means the inverse of y. It's just a name, it's a label. That's it. It's a way to show the difference between this y, this is the original function, this is the inverse function. No, you don't have to. So log base 3 of y minus 2. What do we do? What do we do? Change it to exponential. What's my base on both sides? 3. So 3 to the x equals 3 to the log base 3 of y minus 2. What happens? 3 log base 3 cancels, correct? So this and that cancels, and that leaves me with 3 to the x equals y minus 2. What do? Add 2 to both sides. We need y by itself. So 3 to the x plus 2 equals y. That is the inverse function. I want you guys to try number 3 on your own. Now, for number 3, is that plus 2 in parentheses with x? No. If it wanted to be in with x, it would be in parentheses with x. It's not. That's by itself. So I'm going to give you a hint. Before you change both sides to exponential form, get that log by itself. That log has to be by itself. How do you do that? Subtract 2 from both sides. You have to have that by itself. So you say, well, first you're going to switch x and y. Okay, first you're going to switch x and y. So x equals log base 3 of y plus 2.
No.
Then you're going to subtract 2 from both sides to get that log by itself. You understand? So it'll be x minus 2 equals log base 3 of y. You have to isolate the variable that you're trying to get by itself first. Now, if you want, keep that in parentheses because those two are together. Okay? Now you can change both sides to exponential form. What's my base? 3. So 3 to the x minus 2 equals 3 to the log base 3 of y. What happens? 3 log base 3 cancels, right? So that just leaves me with y equals 3 to the x minus 2. How do you think we're going to approach number 4? Well, first we have to do what? Switch x and y. So we have x equals 5 to the y minus 3. If we're trying to solve for y, I need to get that x, just like we had to get the log by itself, we need to get that exponential by itself. What do? Add 3 to both sides. So this is x plus 3 equals 5 to the y. Keep that together. Now, what do? Take the log base what? What's my base for that? The base is 5. So we're going to take the log base 5 of both sides. Okay? So, log base 5 of x plus 3 equals log base 5 of 5 to the y. What happens? The log base 5 of 5 cancels. Leaving me with just y equals log base 5 of x plus 3. Okay, number 5, y equals ln of 5x. ln is the same thing as what? Log base e. So, change that. Y equals log base e of 5x. Because when you switch it, you need to know what the base is, right? Now we have to reverse x and y. Switch x and y, correct? So, x equals log base e of 5y. Okay, what's my base? E. So I'm going to write the left and right side in exponential form, using e as my base. So, e to the x equals e to the log base e of 5y. What happens? E log base e cancels, right? So I'm left with good. E to the x equals 5y. Am I done? No. What do we have to do? Divide both sides by 5. So y equals e to the x divided by 5. Now try number 6. All right, switch x and y. Well, change it to log first, or regular log. So y equals log base e of x minus 3. Then switch x and y. Change both sides to exponential form with e being the base. So e to the x equals e to the log base e of y minus 3. So e to the log base e cancels, leaving me with e to the x equals y minus 3, and then you add 3 to both sides. So we're going to switch the x and y. So x equals 4 to the y divided by 5 power. Now I'm going to take the log base 4 of both sides. Log base 4 of x equals log base 4 of 4 to the y divided by 5 power. What happened? The log base 4 of 4 canceled. So we're left with log base 4 of x equals y divided by 5. And what do? Multiply both sides by 5. So when we multiply by 5, this cancels. So this is equal to 5 times log base 4 of x. All we did was multiply by 5. So we switch x and y. So you probably got stuck right there if you weren't sure what to do now. You have to have that e to the y by itself. So we multiply both sides by 6. Now, see, we multiplied by 6 and that canceled this. Now, you can take the log base what of both sides? E. Log base e. Log base e of 6x equals log base e of e to the y. Now what cancels? Log base e of e. So we're left with log base e of 6x equals y. What is log base e? Ln. Log base e is the natural log, right? So, although this is correct, you won't see log base e. They won't put that. Just like they won't put log base 10. You'll see ln of 6x equals y. The last part of the section is graphing logs. Now, here's our form. Y equals log base b of x minus h and then plus k. Okay? K represents a vertical shift up and down. H represents a horizontal shift left or right. And because it's in parentheses, it's the opposite. Okay? So if it's x minus 3, then it got shifted to the right 3 units. If it's x plus 3, it got shifted to the left 3 units. Okay? Your vertical shift is irrelevant for this. It doesn't matter if it got shifted up or down. That doesn't affect your asymptote. Now, exponential functions have a horizontal asymptote. It has a flat line, right? Okay? Logarithms have a vertical asymptote. It has an invisible wall that graph will not cross. Your vertical asymptote is normally at x equals 0. It's normally right here on the board. I have a parent graph. So this is normally your vertical wall is at a vertical line at x equals 0. If it gets shifted left or right, it moves that vertical asymptote either left or right. So if it got shifted 3 places to the right, then your vertical asymptote is now at x equals 3. If it got shifted 3 places to the left, then your vertical asymptote is now at x equals negative 3. Okay? It doesn't matter whether it got shifted up or down. That doesn't change where your vertical asymptote is. Okay? So that's why we say x equals h is our vertical asymptote, whatever h is. Now, so I don't care if it got shifted up or down. I only care about left or right. So when we look at this function, this first one right here, where did it get shifted? Right 5 units, correct? It got shifted right 5. So no longer is my vertical asymptote at x equals 0. It's now at x equals 5. All right, for the second one, where did it get shifted? Anywhere? It didn't get shifted anywhere. There's nothing added or subtracted to x. Okay, this negative 4, that's your k. We don't care about k. We only care about left or right. It didn't get shifted at all. There was no left or right shift. So my vertical asymptote is still at x equals 0. Now, the last one, where do you think it got shifted? You think it got shifted right 5. Is there anything in parentheses with x? No. There is nothing in parentheses with x. It has to be in parentheses with x for it to be shifted. They didn't just forget to put the parentheses. They don't exist. This is because this second example I wanted to show you, you could clearly see that it didn't get shifted left or right at all. But that's not how you will see it. You will see it like this. If it didn't get shifted left or right at all, they don't put the parentheses because they're not necessary. They only put the parentheses if there was something added or subtracted to x specifically. So this is the same thing. So there was no left or right shift. So my vertical asymptote is still at x equals 0. They're only going to put the parentheses if they are necessary. So let's look at graphing our first one. First thing you want to graph is the vertical asymptote. Okay, so we have y equals log base 5 of x plus 4. Now, where did this get shifted? To the left 4. So my vertical asymptote is at x equals what? Negative 4. So it's no longer at 0. It's now at x equals negative 4. Okay? Next thing you're going to do is you're going to put it in your calculator and you're going to pick 3 points from the table. One of those points, we're not worried about our where it crosses the y-axis. Sometimes it may not cross the y-axis, okay? You want to know where it crosses the x-axis. The x-axis is your 0 in your calculator. But you're going to go, you're going to put log base 5 of x plus 4 in your calculator. Now, you might be asking, how? Because the base is 5. The base isn't 10, right? You have one of two choices. You could do your change of base. You could do log of x plus 4 divided by log of 5. Or, if you take your calculator, and in your calculator, in the math menu, go down all the way to option A. That's log base. That allows you to change the base manually. So you're going to put log base 5 of x plus 4 in your calculator. Okay. And I'm going to pick points from the table. Once you get in your calculator, go look at the table. And if you can get the x and y intercepts, that's great. The table just shows you that, and that's great. So 1 point is -3, 0. Another one is 0 and 0.86. This is my x-intercept, this is my y-intercept, and 1, 1. So when I plot those, 1, 1, -3, 0, and 0.86 is right here. Now, if you look in your calculator, if you look at the graph, it's going to look like that graph stops. It's going to look like that graph stops. This graph does not stop. Okay? Remember, it's the reverse of the exponential, so it keeps going in both directions. This graph looks like this. It's going to go to that vertical asymptote, and it's just going to follow it all the way down. It's going to get closer and closer and closer and closer to it. Okay? Your calculator looks like it stops right here because it only shows you the increments that are on the table. So if your table is incremental 1, it's only going to show you, it doesn't show you these points in between. Okay? So my domain. How far left and right does it go? How far to the left does it go? It stops at -4, right? And how far right does it go? Forever. So my domain, x greater than -4. My range, how far up and down does it go? Forever, all real numbers. It's the opposite. So now we have a restriction on x, but not y. Okay, so I'm going to finish that second graphing example now. Okay, so remember, L and X is just the same thing as log base E of X. Okay, and they did not put that in parentheses, the X minus 1. So that means X is by itself. So that means it didn't get shifted left and right at all. So my vertical asymptote is still at X equals 0. So it stays where it is. Okay? Now, we go look at our table. And at x equals 0, this says error. That's because x cannot be 0 because that's from my asymptote. We got another point, 1, -1. So 1, -1 right here. All right, I see that 2 is -0.3. I see that 3 is 0.09. What I need to know is I need to know where it crosses that x-axis. I need to know the x-intercept. And at the x-intercept, y is 0. So what you can do is you can do second, calculate 0. And your left boundary, you can choose to be, say, 0. In your right boundary, you can choose x to be 10 and tell it to guess. And so it says that's the point 2.7 and my y coordinate is 0. So I'm going to graph that. So 2.7. So 2.70 is where it crosses the x-axis. Here's my x-axis. I can plot some of the other points in between. So 2, negative 0.3, it's right here. 3.09, it's starting to get a little bit positive. And so my graph looks like this. Now, the domain, how far left does it go? Well, it starts at 0, and then it goes all the way to right. So my domain is all the x's greater than 0. My range is all real numbers. It goes up and down forever. So you need to have this point plotted, and then any two of the other points, it doesn't matter. But you need to at that point.